I really have been looking forward to this colloquium, and I think you all will find it really inspiring and hopefully will generate a lot of questions. So the focus of the talk, it's extremely important to what we do here at Argonne, right? We're about energy, and we've been thinking about it since our inception in 1946. And we do science and engineering to figure out what to do about solving energy, environment, and security challenges, and thinking about energy as it links to our environment and things like climate change, and just in general the state of our environment, like greenhouse gas emissions, like soot in the atmosphere, et cetera. So this is clearly a pressing issue for the United States, the globe, and thinking about how to solve our energy challenges. And the question that always comes up is, do we have to continue to rely on fossil fuels? Fossil fuels, of course, injects a tremendous amount into our economy. And so should fossil fuels and economic growth be linked, or is there a way to break that link? And sort of, in some cases, when you're using all these fossil fuels, what are you really doing to the environment? But today, we're going to hear from a world expert and a great friend of the laboratories and of science related to energy, Dr. Arun Majumdar, who's going to argue that we can actually do this in a way that continues to drive economic development as well as protecting the environment. He's really in a unique place to have that perspective. He came from Lawrence Berkeley National Laboratory, where he was a scientist, a very accomplished scientist, as well as a division director, and ultimately an associate lab director at Lawrence Berkeley Lab, up until he got the phone call from Washington. And in the last term of the Obama administration, he actually became the founding director of an agency that I think many of us are aware of, the Advanced Research Projects Agency for Energy, ARPAE. So he was the founding director of ARPAE and provided tremendous leadership at the time in Washington to basically stand up an agency from nothing that is now doing really transformational research in the energy space, across all the energy space. In his spare time while he was back there, he also ended up being the acting undersecretary for energy while he was there. So he was running ARPAE and also acting in that position. So he had two very important jobs, provided tremendous leadership, and the labs actually do miss him, his presence in Washington. But he decided it was time to go back to California. So he's currently the vice president for energy at Google. That's his current position, where he advises the Committee on Energy Strategy and Initiatives. So I already mentioned that he's an outstanding scientist as well in his own right. He's a member of the National Academy of Engineering and the American Academy of Arts and Sciences. And his research career focused on the science and engineering of nanoscale materials and devices, as well as large engineered systems. So please join me in welcoming Dr. Majumdar to Argonne today.
Thank you. Well, thank you for the very kind introduction. I usually introduce myself as a recovering government bureaucrat, and so that was very kind and generous. It's a real pleasure to be here, and whenever I've visited Argonne in the past, it's really been a learning experience, and there's so much of really interesting science and engineering that's going on out here. And it's, as I said, it was always educational. So it's delighted to be back here. So I'm going to talk about energy and the Industrial Revolution. And they are obviously, as you well know, very well correlated. But I want you to step back for a moment and go back to when the United States was being created. The Revolutionary War, the times of George Washington and Thomas Jefferson, and just try to think about what life was like. You always see paintings of George Washington on his horse and, winning the war. And that was the mode of transportation. And if you look at what was the mode of lighting, you had lamps like that, which was basically run by whale oil, because petroleum was not yet discovered. That was in 1862 when they dug a hole in Pennsylvania and oil came out. And so that was what life was like. And the last 240 years of the life of the United States coincided with probably one of the most incredible periods of human history. because it was that time that the world transitioned and innovation happened into what I would call from the horsepower to horsepower. And today we go to the grocery stores or we drive around with 300 horses taking us there to the grocery store. Or I flew from California to Chicago day before with 100,000 horses in 4 hours, what would have taken about a month during the times of Washington and Jefferson. So that's the transformation. And human history is about 10,000 odd years old, a little bit more. And in that 10,000 years, the last 250 years is when all of this happened. And we light our homes not by whale oil anymore, but by a grid. And if you look at this world today, I don't think Washington and Jefferson could have imagined this lifestyle that we have today. And so obviously this has changed the world in many ways. It has increased our productivity. It has increased our prosperity. And that has been an exponential increase. And it's measured, in this case, by global per capita GDP. This is global now. And you could have multiple measures, but this is one. And that has increased exponentially, and so has our energy use. And if you look at this, almost all of it has been, 80% of this has been fossil energy. And so the Industrial Revolution is all about energy. How we source energy, how we distribute energy, how we use energy. That's what it's been. There are a few other exponential increases that happen. The world population went from 700 million people in the beginning of the Industrial Revolution to 7 billion. So 10x. And that's a factor not just of the Industrial Revolution, but of things like the Haber-Bosch process that made artificial fertilizers that help, save the world from starvation and famine and grew food for all of us. And so this is now the world that we live in. We have 7 billion people. By 2050, the estimates are 9 billion. And by 2100, 10 billion, plus minus an error bar. And that number really depends on the fertility of women in Africa. That's what it depends on. And so this is the world we're going to encounter in the future. Our children, grandchildren are going to encounter. So if the first 250 years has been fueled by fossil fuels, and this is the number of people, and we want the economic growth to happen, the question is, do we have enough fossil fuel to support our population and economic growth? And the answer seems like it's yes. Because these are the global oil reserves on the left-hand side, and you have the global gas reserves. This is not counting US shale. And you find that there is no peak. And people talk about peak oil. There's really no peak. And that is because the technology for discovery and extraction gets better and better, gets cheaper, and it keeps pace. And in fact, not only keeps pace with the demand, it exceeds the demand. So sometimes you find the capacity is built out and the price comes down. But there seems to be enough fossil fuel out there. In fact, right now, we are all excited about US shale. We haven't even touched methane hydrates, and there's a lot more out there. So it's fair to say we have a lot of fossil fuels. But if we are to extend this word, there are a few things we should be aware of that we are encountering today. And that is, you have these the global price of oil. One of the things that amusing things we had to encounter in Washington is that everyone blamed the president for the price of oil. The president does not control. In fact, we had to put up a nice face in hearings and all that, saying that we're really sorry the price of oil is low. We had no control over it, neither did Congress. Neither does Congress. But this is, if you look at the price of oil, you are looking at all these fluctuations. And this unpredictability of the price of oil is an economic security issue. And $1, even 5 cents or $1 per gallon change is a big deal. Billions of dollars are at stake out here. And all these fluctuations that you're seeing, none of them were controlled by what happened inside the United States. In fact, almost all of them happened because of events outside the United States. So we have to be aware of this, that if you are to enter this world and continue as business as usual, there is this uncertainty that is there that we should be aware of, and that really affects our economic security. Of course, we are importing oil, and over the last several decades, for the first time, we are producing more in the United States than we're importing. And that's a great news. But we're still importing 40+% of our oil, which accounts to about $300 billion a year of balance of payment. And that's roughly $1 billion a day. That's a lot of money. And in fact, we would rather have that be spent in the United States for our own economic growth than send it somewhere else. And we are not alone in this. China is in the same boat. India is in the same boat. Germany is in the same boat. Japan is in the same boat. So this is a global problem, that the dependence on fossil fuel and dependence on oil for transportation on a single fuel is a vulnerability that the world faces. And so everyone is trying to get out of this in some way. So you got an economic security issue, you got a balance of payment issue. Of course, these are all related to national security in some way. And of course, we have an environmental problem. And we all know that from the beginning of the Industrial Revolution, the average temperature of the world, and this is just first law of thermodynamics. People who say there isn't global, it's just first law of thermodynamics. You got more radiation coming in than going out. The temperature has to go up. And the average temperature has gone up by about 0.8 degrees Celsius. But the average, if I go on the streets of Chicago and say that the world has warmed by 0.8 degrees, most people would say, most layperson would say, so what? Because my bedroom changes by 10 degrees over a day because my insulation is bad. So it's not the average is important, but there's much more than just the average. And I'm going to show you the distribution, because the average just gives you one number, and it's really important to pay attention to the distribution. And I'm going to show you the distribution which changes. It's the deviation from the average that I'm going to present to you. And in some times, some summers are hotter than others, the average. Some summers are colder. And we face this all the time. So if you plot the data averaged across the world on the deviation, one would expect that this distribution follows a Gaussian distribution. And it does. So I'm going to show you the data. First, the theory, which is a simple Gaussian. And on the right-hand side, you're going to see the red, which is hot, and the left-hand side will be blue, which is cold. And it's normalized by the standard deviation. So 1 sigma, 2 sigma, 3 sigma. So this is what it looks like. But now I'm going to play the movie for you as to how this distribution, this is data now, of the 1960s and 70s. You can see this is fluctuating, but it's about the Gaussian, and see what happens. So clearly the average has moved, but that is just a small slice of the whole story, because what you're finding is that this distribution is broadened. There's clearly a direction for this distribution to move. It is not moving on the other side, but the tails of the distribution, which has a nonlinear effect on our life, on our economy, is certainly there, and you're reaching 4 to 5 sigmas, 4 to 5 sigmas at probabilities that were unheard of in the past. And it is this tail which is really worrisome. So last summer you had a heat wave in the Midwest, which was almost as bad or worse in certain cases than the Dust Bowl of the 1930s, which led to a lot of folk music and all that, right? And so, and last year, it really affected our agriculture and our livestock, et cetera. A few years ago, we had this heat wave in Moscow and Russia, which killed about 70,000 people. Before that, it was in Europe. So if you really look at the geographical map, I'm not presenting out here, but there's a geographical map. And what you find is these heat waves, the spots, the hot spots, are moving around the world, just like a bubble in a carpet. We don't know where it's going to happen next. And so climate change, there's a lot of science that is needed to figure out where it's going to happen next so they can plan for it. But certainly this is happening, and it's going around, the hot spots. So this is a real issue. So now if you ask the questions, you got economic security, you got a balance of payment, now you got an environmental aspect of it. So let's go back to the beginning of the Industrial Revolution and ask the question, how much CO2 have we emitted since the beginning of the Industrial Revolution, which has given this 0.8 degrees rise? So what's the cumulative CO2 emissions since the beginning of the Industrial Revolution? And this just came out in an IPCC report, and I'm going to put some rough numbers out there, approximate numbers. And it's about 1 trillion tons of CO2. And the life of the CO2 molecule in the atmosphere is more than 100 years. In fact, most of the CO2 molecules are still there. Some of it is absorbed in the oceans. But nevertheless, it's still there. It's like a big capacitor, and it's integrating over time. So this is 1 trillion tons in 250 years. So then you ask the question, based on the known reserves of fossil fuel today, which, by the way, keeps on increasing because the technology improves and gets cheaper, but based on today's known reserves of fossil fuel, if you take all those fossil fuel and just burn it, how much more CO2 can we emit? Right? So this is the question. How much more CO2 can we emit based on known fossil fuel reserves if you burn it all? And the number is about 3 trillion tons, which keeps on increasing over time. So 3 times more than before. The first trillion, 250 years, you ask the question, based on today's economic growth and a use of fossil fuel, how long will it take to produce 3 trillion tons of CO2 and emit if you burn everything? And it's shockingly small. It's 75 to 100 years. So you got 3 times more CO2 in about roughly 1/3 the time. So it's almost a 10x factor that we're looking at in the future. And then you ask the question, these 3 trillion tons of carbon in terms of fossil fuel, how much is it worth? What's the dollar value? And the number is tens of trillions of dollars. People are estimating $28, $30 trillion, but it's a huge number. So society is given the choice. The choice is as follows. Should we keep those 30 trillion or tens of trillions of dollars in the ground and not use it for economic growth and save the environment? Or should we take those tens of trillions of dollars, continue on the exponential growth of our economy, and to hell with the environment? And that is the choice given, and that is a false choice. Because what people don't account for is the ability for the human mind to innovate when there is a need. And this is best articulated by the former oil minister of Saudi Arabia when he said, "The Stone Age did not end because we ran out of stones. It's because we transitioned to better solutions, which is why you are needed, which is why research is needed, which is what Steve Chu and I wrote in our paper that came out in Nature last year. It's really calling for a new industrial revolution. If the old industrial revolution was all about using fossil fuel, it's all about energy, but it was based on fossil fuel. Could we have a new industrial revolution which really accounts for all the 3 securities, the economic security, national security, as well as the environmental security? And I'm going to show, since I'm a part of Google, I'm going to show only one slide for Google. What are we doing about it? So Google is a 100% carbon neutral company, 100%. So what do? The 3 steps. One is we use a lot of electricity in our data centers and our computers, and we make them as efficient as possible because it saves us money, and it saves the environment, in both. Secondly, we're investing a lot in clean energy, clean electricity. And we have invested so far in project finance about $1 billion, mostly in the United States, and now we have gone overseas in South Africa, and we're going to go overseas more. in clean electricity sources. And so that's the investment, and this is not charity. This is for returns, because there's money to be made out here. And finally, what we cannot help, we offset, so we pay more. In fact, we have started what is called the green tariff. We created a different tariff structure with the utility in North Carolina so that we can integrate more electricity from renewable and clean sources onto the grid, and we're willing to pay more. So that's what's going on in Google. Now, what I'm going to present is mostly what I learned at ARPAE. So just a few words about what is ARPAE? What was the mission? In the energy business, the things that really matter is a technology that scales in volume over time and scales down in cost. If the cost does not come down, and if a technology doesn't scale, it doesn't matter. So the best way to present it is using what are called learning curves, experience curves in economics. So any technology, in this case, you have an existing technology, I'm going back to the early 1900s, which is a horse carriage, in this case, for transportation. And that's an existing technology, and that improved over time. And in the beginning of the 20th century, this was the technology of use. And you can improve this technology. You can make better bearings, you can make better wheels, you can get stronger horses. And you can improve this. And what happened at that time was some wild and crazy ideas to be disruptive, to be transformational and disruptive to this technology. And that was automation. These were, there were many ideas, steam-powered, vehicles and the Benz motor wagon. And there were multiple shots at goal to be transformative, and only one of them succeeded. In this case, well, there are many, but one of them really succeeded. That was a Model T. And Model T, all of these were transformational, potentially. But one of them became disruptive because it was cheaper, it was faster, and frankly, it was cleaner because people didn't have to clean up all the horse poop on the roads, which was a big environmental issue in cities like New York. So it was cleaner, it was faster, and it was cheaper. And so this is what transformative and disruptive could do. It creates entirely new learning curves in the whole business of energy, and eventually the technologies become, the existing technologies become obsolete. And that is really the role of ARPAE, to take multiple shots at goal, to be both transformative and initially may seem crazy, but one of them may succeed. But bring it to the energy business to address the three securities, as well as to provide US with a technological lead, because if we don't do it, someone else will. And so that was the whole idea. So I'm going to talk about a few examples of this, but it's best to say that in the context of our energy system. And the energy system is really two different systems. One is the stationary system, which is the electricity generation, electricity transmission and distribution and reuse, and natural gas to our home. This is the stationary power system. And the other is a transportation system, which is mostly petroleum, gasoline and diesel, and used in cars and trucks, et cetera. And these two systems really don't talk to each other, except more recently because of electric vehicles, but that's a very small percentage of our transportation system. So first I'm going to talk about the stationary system. And what has happened in this case is, over the last 5 to 7 years, there has been a disruption that I just talked about. And it's taken the existing learning curve and just become better and cheaper. And that is the use of shale gas, the natural gas. So I'll just say very briefly about what that is all about. This is how shale gas is produced. Most people in the 1980s, which is when it was funded, it started in the 1980s in the Department of Energy. It was thought to be a crazy idea, is to go deep about 7,000 feet to the shale formation out there and drill horizontally and use hydraulic fracturing to fracture the rock, because these are highly impermeable, and so you want to increase the permeability. Again, shale was ignored by most geologists and geophysicists because they just had to drill through it to get to the sandstone to get oil and gas. And so everyone ignored it, except for a few crazy guys who said, okay, let's go for it. And to their credit, DOE supported that. So now this, over the last 7 years or so, this became economical to produce gas at scale. And so that's why this shale gas revolution, but it took about 25 years or so to get there. Now, there's a lot of euphoria about natural gas, and understandably so. But I'm going to show you a little bit of the science and engineering that is needed now, because since shale was ignored, even by the geophysicists and geologists, for a long time, there's a lot of learning that is going on. So I'm going to show you the coupling between chemistry, transport, and mechanics. And this is some data on the production, on the extraction of shale gas. And on the vertical axis is the rate of flow rate. Horizontal axis is over time. And when the wells were dug, wells started producing natural gas in the 2005, 2004, this was the peak. It peaked out there, and then there was a tail. And over time, the technology improved so that the peaks went up. But what is happening is that there's this tail, and we don't have any idea right now as to how long this tail is going to last and what shape and form it's going to be. No one really knows this. And why is it so? Why is it so hard to predict that? It's because if you look inside the shale rock, this is what it looks like. You got these pores in there that are 10 to 100 nanometers in size. And this is the inorganic material is covered with an organic, really long-chain hydrocarbon organic material called kerogen. And adsorbed, and that's what the spores are all about. And adsorbed on this layer of kerogen is the natural gas or short-chain hydrocarbons. And it follows Langmuir isotherms. Okay, so we know how it works. But the pore size, the permeability of the pore, which depends on the size, depends on the square of the size, really depends on the pore pressure. So you got now the permeability depending on the mechanics of this material. So there's a coupling between the chemistry, which is the physisorption of these gas molecules on the surface, and the transport and the mechanics. Now, it turns out that in the oil and gas industry, the computational models that are used to model this, that coupling is missing today. So there's some real work that is required out here. And because the size is 10 to 100 nanometers, the flow is not viscous, and many times is Knudsen flow. And because of Knudsen flow, and we don't know when that transition happens, we really do not understand fully, capture the science of the fluid mechanics and the solid mechanics, as well as the chemistry, coupled together. So this is a real problem, and I hope the scientists and engineers really get into it, because not all shales are equal. The Marcellus shale and the Barnett shale, we can put pressure with water, you can fracture it. But there's Floyd shale in Alabama that we cannot fracture because the clay content is too high. And because, as some of you know, clay is a two-dimensional material. You try to fracture it with water, and it just slides. It's viscoplastic. So there's a lot of work still remaining to be done to understand shale. So while we should be very happy, and it's nature has been very kind to the United States to provide this resource, which we should use judiciously, and we have a lot of it, but there's an error bar out there that we don't talk about, and we should be aware of that as well. But what has happened so far, because of the abundance and low cost of shale, the price of shale gas, or gas, has separated from oil that was coupled together, because it's now shale or gas is a local economy because we don't have enough global transport of gas. And because of the low price, it is displacing coal, purely because of economic reasons, displacing coal from electricity generation. Electricity used to be 50% from coal. Today it's about 30-something%. And natural gas has replaced that and become about 30%. Why? Because the cost of production of electricity is about 5 cents a kilowatt hour. That's the cheapest way to produce electricity from natural gas combined cycle with gas. Now, the gas price is low, and the combined cycle turbines
the efficiency is about 60+%. This is from GEs and the Alstoms and the Siemens, 60+%, and these gas turbines ramp up at about 50 megawatts a minute. And so they can firm up wind turbines, et cetera, as well. So it's a base load as well as ramping for firming. And this is a tremendous technology, and it creates the benchmark for other electricity generation. So where is the other source of electricity? Well, you have geothermal coal, nuclear. We just started a lot of nuclear after 30 years, not a lot, enough, but after 30 years, first few nuclear plants are being built. Hopefully we'll get small modular reactors in the future. This is really important for addressing climate. But there's also renewable electricity, which is wind and solar. And wind, in many cases, is cheaper than coal today. And the price is even going lower. I'll show you some data on that. And there is solar, which is a little more expensive, but it's coming down fast. And in DOE, we created something called the Sunshot Initiative, just like President Kennedy had the moonshot to go to the moon and return safely within the decade. The sunshot is not to go to the sun and return safely, but to reduce the cost of electricity production from solar to 5 cents a kilowatt hour, unsubsidized, by the end of this decade. And I think there's a good chance we'll reach there, if not by 2020, by 2022 or so. So I'm going to say a little bit about that, but there's a big difference between these kinds of generation. These are all centralized generation, which is amenable to the grid of today. But these are distributed and modular, and the grid has to adapt to it, and I'll come to that in a few minutes. So this is now the cost of electricity production from wind, which has really come down, and this is sort of the installed wind capacity. It's about 50 or 60 gigawatts. And frankly, this is, on the big scheme of things, the US capacity for electricity is about a terawatt. So this is a small percent, but nevertheless, you can see the trend, and it's actually quite nice. It's exponential increase, and the price has come down, or cost of production has come down a lot. But there are some things in here that are worrisome in terms of technology. And it's not so much the wind turbine, but the mechanical to electricity conversion, mechanical energy to electricity, and that is done by generators, which use large magnets. And these magnets, permanent magnets, are based on rare earths. These are iron boride magnets which use neodymium and dysprosium. Neodymium to create the crystalline isotropy to create the strong magnets. And rare earths, 90% of those, 95% are sourced from China. And we have a supply risk because of the fact that there's internal demand in China, and they might actually like to use it. So there was a lot of effort in looking at rare earth, and there's a whole energy innovation hub on that. But before that happened in ARPAE, we said maybe we should look at that and see if there are other technologies. And it turns out if you go back to the 70s and early 80s, there was a lot of research done on magnets before iron boride, neodymium-based iron boride magnets came around. And those were ignored because neodymium-based iron boride became the magnet of choice. And so this is one type of material. This is, I'm sorry, it's getting cutting off. This is iron nitride, iron-16 nitrogen-2, which has a huge anisotropy in the crystal, which creates the energy density of this is actually higher than iron boride magnets. The problem is that these can be created in thin films, and there are 3 groups, one in Minnesota, Oak Ridge, and Case Western. They had all done this in thin films because of data storage needs, et cetera, but no one had done this in bulk. So we went in there and said, okay, can you make this magnet, which is rare earth free, with earth abundant materials available in the United States, and can you make this in bulk? And they are now looking at it, they're going after it, and they're having a little bit of success in this. So this is a materials issue, but materials and manufacturing issue with some science built into it. On the solar side, this is now the cost of a PV module in dollars per watt. So this has come down significantly, and now you can get modules on the order of 60 to 70 cents a watt. But the module price is low enough to the point that the fully installed cost of solar at the residential scale is about $3 to $4 a watt, whereas at the utility scale, it's about $2 to $2.50 a watt. So the most of the cost today for solar is really not in the panel, but in what is called the balance of system. This is the installation, this is the permitting, the whole process. There's a technology aspect as well, but it's a technology plus process aspect. In Germany, it's much lower, the balance of system cost. This includes, by the way, power electronics as well. So the question is, how can we reduce this? Because if you can get to $1 a watt fully installed, you get to the 5 to 6 cents a kilowatt hour. So how do we get these numbers down here and this number down here as well? Well, and are there any technological knobs to get there? And there are two technological knobs out here. One is the weight. If you could reduce the weight and do this on thin film, on lightweight material, that's a big deal because installation becomes much easier. And the second is the efficiency of these cells. So this is now the efficiency on the vertical axis and different technologies. And this red line out here is what is called the Shockley-Quasar limit. The practical aspect of Shockley-Quasar limit is roughly 30% for most single junction, semiconductor-based photovoltaics. And if you look at the production level of silicon from sun power, et cetera, you get about 24% or so 24, 25%, and there's a little room out here, but it's not that much, and we're getting there. On the other hand, polycrystalline silicon, SIGs, and cadmium telluride, they're roughly about 13 or 14% at production level, and there's plenty of room at the top. And the research is really needed to understand how to increase the efficiency so that you can get better material, remove the dislocation, reduce the dislocation density, improve the contacts and the surface interfaces so you can increase the efficiency of these cells. And as part of Sunshine, we started something called the Michael Jordan Initiative. Now, I'm in Chicago. Michael Jordan is, of course, a big deal. Why Michael Jordan? Because we wanted to increase the efficiency of cadmium telluride to 23%. And people loved it, and they're going after it. Because if you can show 23% in the lab, there's a chance you can get to about 17, 18% in production value. And if you can get to that kind of efficiency, it's a game changer. But that's not enough. I mean, these are existing technology, but there's some left field technologies as well. This is 3,5 material coming out of Alta Devices. This is a company that's started by Harry Atwater, Eli Jablanovic, and they have shown 28.8% efficiency on single junction cells. They've shown 30-something% in multi-junction cells, and they're doing it in single crystal 3,5 material on plastic. And this is a big deal, because if they can get to 25% at production level, this is a game changer then. So there are lots of these other things, and there's plenty of room still there for the cost to come down. Now, of course, these are intermittent sources. Integration on the grid is a challenge because our current dispatch process that we have in our grid is really not amenable for things that are fluctuating. They want to have certainty in the dispatch process. So storage is a big deal. And I don't have to tell this crowd how important storage is. You guys have the hub out here. But there is some cost target. And this is where science and engineering has to come in, not only from understanding the chemistries, et cetera, but also understanding the system level to bring down the cost. And the first cost, there are these, there's a log scale out here. What is the capital expenditure for grid level storage? The first cost is important. And the target is really $100 a kilowatt hour, because that's what pumped hydro is about $100 a kilowatt hour. So if you really want to compete, well, it'd be great to have it geographically distributed all around the world, but you have to really compete at the cost as well. And you need science and engineering to get there, whereas many of these technologies that were out there, flow batteries and others, were on the order of $400, $500, $700 a kilowatt hour. So we created a program in ARPAE to go for those technologies and really do the research so that they would eventually be $100 a kilowatt hour in the future, or $150 a kilowatt hour. So what are those technologies? There are plenty. Again, multiple shots at goal, a whole portfolio of approaches, and all competing with each other. So I'll give you a few examples. This is from City College. This is zinc manganese oxide. These are not flow batteries. These are batteries. Again, it's not just the first cost that is important. It's important, but the cycle life, the number of cycles you can get out of it, as well as the calendar life, the round trip efficiency, all of these are important. And so they had shown roughly $300 a kilowatt hour. They're going towards $100 a kilowatt hour. Arizona State University, this is Cody Friesen and his team. They've developed zinc air rechargeable batteries in a flow battery sense, and they've transitioned that to fluidic energy. These guys are now piloting their batteries in Indonesia, which is that's where the market is right now. There's, of course, 24M, came out of Yetmin Chang's group, that they've taken the best of the chemistry of lithium ion, put that in a flow battery architecture so that the system cost goes down, and they're targeting $60 a kilowatt hour, which is really aggressive. Why 24M? Because the molarity of lithium in these electrodes is 24 molar, and that's why 24M. And Primus Power looking at zinc-based battery. So they're all competing, and there are many more out there. They're all competing. And they all have to understand the science of what's going on in these electrodes, what's the electrolytes like. And there's a lot of science and engineering still remaining. And I'm hoping, and I understand, the hub is going to help them to really understand and reduce the cost and improve the performance even more. But these batteries are required for grid integration. It's really important to understand what the grid is all about. Now, the grid started in the United States. It is called the greatest engineering achievement of the 20th century by the National Academy of Engineering. But if you step back for a moment, it was the 20th century. And if you look at the architecture today of the grid and the paradigm, the architecture really goes back to Tesla and Edison. The architecture has not changed. And the paradigm is the following. You got centralized generation of electricity. Why centralized? Because it is cheaper. The economies of scale for thermal power plants and hydropower plants. And then you have, and these are typically away from population centers, so you need high voltage transmission long distance, and then you go to the local substation where you have a distribution network and feeder lines into neighborhood at 13 kilovolts, and then you tap into it at 240 volts, and you use 120 of those. That's been the architecture, and that has not changed. And this architecture is we have $1 trillion of assets on this, and those assets are aging. And just to give you a number, we lose roughly $100 billion a year to power outages. And the rough numbers are about 1.5 to 2 hours the average is 1.5 to 2 hours per year. That may seem small, but the tails of the distribution kill you. And so, for example, what happened in Superstorm Sandy is that hundreds of thousands, 600,000 people lost electricity immediately, and after 2 weeks, roughly 50,000 people still did not have electricity. And if you really go and find out what happened, is the distribution network really got messed up. And so there's a vulnerability out there, and a lot of people are looking at what the grid will be like in the future, and is there a different architecture that we can have. But there's a security aspect as well, and a lot of people, the ISOs and utilities, are worried about security. I'm going to give you one incident that sort of highlights the vulnerability. And I don't want you to get scared from this, but it's important to note what could happen. And it's not just cybersecurity, but cyber-physical security. And this was highlighted by an incident that most of us don't know about. I didn't know about it till I learned about it. And this happened close to where I live, in San Jose, just south of San Jose. If you look at the Highway 101, this is San Jose out here, and if you go towards Almaden and Morgan Hill, there's a big substation called the Metcalf substation, where all these huge transmission lines come, and there's a distribution network, and the substation then feeds into the distribution network up there. And it's very visible along the highway if you're driving down. Now, it turns out that at 2 a.m. on April 16th, there were gunmen at night who went there and identified, probably using thermal cameras, the energized, the active transformers, not the passive ones, and took guns and shot exactly where they needed to shoot, at the radiators of these transformers, where they could leak out the cooling oil. Mineral oil is used to cool them, and the 50,000 gallons of oil were leaked out because 13 of these were shot at, and so that the transformers would trip. And as bad as it may sound, it's worse. because 15 minutes before that, they went to the level 3 vault where they cut the fiber optic and telephone lines so that 911 was disabled. And no one heard about it. I live around this neighborhood. I didn't hear about it. Why? Because it happened within 24 hours of the Boston Marathon bombing. So when the whole media was focused on Boston Marathon bombing, these guys were doing something. I don't know what the purpose was, clearly, to figure out how vulnerable we are. They haven't been caught. Homeland Security, I'm assuming, I'm praying, they're looking into it. Ernie Moniz, the Secretary of Energy, talked about it just last month when we were together. And this is a big deal. And if this can happen, this is not just Stuxnet. This is more than that. This is the physical side of it. There's a lot more vulnerability that could be exposed. And we are really exposed right now in many ways. So this is a real issue, and we need to make our grid much more resilient. So what have we done so far? We talked about smart grid, et cetera. So what is this? Because it means a lot of things to a lot of people. So far, what has happened is that we put in a measurement infrastructure. In the transmission network, these are called phasor measurement units. We have about 1,000 of them, which measures the current, the voltage, the phase angle, the frequency, and which is time-stamped, as well as geographically, the GPS on it, geographically stamped on it, and the data is provided every 30 milliseconds. So we have all this data coming out, and we are getting petascales of data. Okay, this is a big data problem. And we really have not figured out what to do with it. And this is on the transmission network, and on the distribution network at the end use, we have not all, but some smart meters that are giving us data in an automated way. And the utilities are trying to figure out what to do with it. So we are at a very early stage of this whole smart grid thing, because how to extract useful information out of this petascale data is yet to be done. What is useful information? Well, we definitely want to understand situational awareness, real time. If some line is getting congested, instead of using pricing mechanism to reduce the congestion, how about routing the power? We don't have routers today. So in ARPAE, we created a program to create routers and to be able to optimize the power flow. And that's happening right now. And how about doing some real-time markets? Because most of the electricity that is coming here today was planned out yesterday. So it's a day-ahead market and day-ahead planning. Well, what about real-time? Why can't we have demand response that we are trying to do, but also supply response? Let the information, instead of having a one-way power flow, which is great, but how about having a two-way information flow so the loads and generation are talking to each other and optimizing in real time so that it behaves like a stock market and not a day-ahead market. Stock market is real time. And these are still remaining to be done. And there's a system-level issue, there's computation, there's optimization problems to be done in real time. Some of the problems are NP hard. Well, maybe you could address that in a confined way, but there's some device-level things as well that could be done. And one of the areas that we really focused on in ARPAE is power electronics. This is converting power, going from low voltage to high voltage, AC to DC, DC to DC, AC to AC conversion, using electronic means as opposed to transformers, which are essentially magnets and coils, which is wonderful, it's cheap, but you really can't control it very well. And so power electronics is a switch mode power electronics. These are switches typically made today it's silicon, but hopefully we'll go into wide bandgap semiconductors because the frequency of switching can go up then. And frequency is important because in a power conversion system, you not only have the switches which operate at kilohertz, hopefully higher, but you also need to then create the 60 hertz. You got to filter out the high frequency. And those filters are made by inductors and capacitors. So if you increase the frequency of the switch, you see the impedance, if the frequency goes up, the inductor size can go down because the impedance remains the same. And if the frequency goes up in the capacitor size goes down. And if the sizes go down, the cost goes down. So the system level cost goes down. And you can optimize them. And this becomes smarter because you can send in signals to be able to control the 60 hertz. You can do phase angle control very easily today. So this is now the area that we focused on. And there's a lot of things that happen. I'm going to give you just one example amongst many on the solid-state transformer, the electronic transformer. This is what the technology is there today. This is about 1 megawatt in a distribution substation transformer. This is about 8,000 pounds. You need a crane to install. It operates at 60 hertz. This is almost the same technology that Tesla had. And the average age of these transformers in the United States is 42 years. And the expected lifespan is 40 years. So we're living on borrowed time. There's a backlog of these transformers. These are the same ones that were shot at. The backlog of the transformers is anywhere from 6 to 24 months. I get different numbers from utilities, but 6 to 24 months. And so people are stockpiling now. This is, we don't just have nuclear stockpile, we have transformer stockpiles. Because people are stockpiling, because if something goes wrong, we need them. So this is the state of today. So we said that maybe we could change that in a certain way, and I'll give you one example of this electronic form, and this is the company called Cree, which is making silicon carbide-based transistors, and this came out of an ARPAE project, where a single transistor could drop 15 kilovolts of voltage across a 200 micron layer thick of silicon carbide. So the material quality has to be really good. You can't have dislocations and resistance, because then you have latch up in these transistors. And it can handle 100 amps. So 1.5 megawatts of power being switched at 50 kilohertz going through a fingertip. That's equivalent to 200 homes. Now, this is the heart of this system now. Now, you take these transistors, put them in bridge circuits, whether you have 4 of them or 6 of them, depending on the number of phases, and you have these LC filters, and now you have power conversion that can happen. And if they operates at 50 kilohertz, the size of the transformer could potentially be 100 pounds, the weight, and it becomes smarter. So that's the technology. No one has really built a transformer yet electronically, and that's what's going on right now. And this is just the silicon carbide. There's a whole gallium nitride thing that's going on as well. But it's important that there's some materials issues out here, not just in the switching material. By the way, we have the 3 largest manufacturers of silicon carbide in the world, right here in the United States. So this is a strategic move that we had to make. So let's go for these wide bandgap semiconductors like silicon carbide. The material aspects really comes in the magnets. So as you go up in frequency, as many of you know, the losses go up, because the losses come from 2 means: your domain walls moving in the magnets, as well as the eddy current losses. And as you go up in frequency, losses go up, and we really don't understand the trends very well. We don't understand soft magnets, because the federal government never invested in soft magnets. They invested in hard magnets because of data storage. But soft magnets are critically important for power conversion. So how do we make magnets which are soft, with a very low hysteresis, and also that can be done at cost? Maybe some nanoparticle-based, and there's a lot of work going on in this, laminates and nanoparticle-based that are insulated so the eddy current goes down, and single domain particles. And so these are now a lot of work that is needed out here to integrate these with the switches and make power conversion circuits. This is where the bottleneck is today. I'll talk a little bit about transportation very briefly. And as you know, predominantly the transportation is based on fossil fuel, gasoline, and diesel as a single fuel, and internal combustion engines. And this is a little worrisome, because we are vulnerable, as I pointed out earlier. There are other sources of fuel, and natural gas is being used now in long-haul trucking. It's economic. We really don't have to subsidize it, both from the trucking side as well as the infrastructure that is being built out by the private sector. I'll talk a little bit about electricity and biofuels. As you know, you all are very much part of this. This is now the battery cost in terms of dollars per kilowatt hour that we are seeing the trend, and the uptake of electric vehicles. There's a lot of work still to be done. And today, if you look at what the technologies are for batteries, really the focus is on the battery, because that's where the bottleneck is. This is lithium-ion in terms of practical energy densities. This is out here, and the cost is roughly $500 a usable kilowatt hour. And ARPAE, we said that maybe we should focus on beyond lithium-ion, and some of these ideas came around in discussion with the Argonne folks. And so the target was $250 a kilowatt hour and beyond lithium-ion. This is a program called BEAST that Dave Danielson, who is now currently in EERE, Assistant Secretary, he created this program. And these are various technologies, whether it's rechargeable zinc air, magnesium ion, advanced lithium ion, as well as lithium sulfur and lithium air. This is not that we started this, these have been tried out before, but there's some fundamental science issues that are still remaining to be done to make them usable in a way that is actually economical. And there's a lot of research still to be done, and I'm hoping that the hub will address them as well. Just to give you one area where the research is remaining to be done is something that you all are very familiar with. That is the technology that NVIDIA is developing, where this cathode material really was developed out here. These are the layered compounds of manganese-based cathode material. And while there's a lot of work that is still going on, NVIDIA decided to add some silicon anodes. And silicon, as many of you know, has some challenges. When lithium goes out, it really distorts the whole lattice and makes it amorphous. So there's a mechanical aspect to this. There are a lot of side reactions that happen in silicon with the electrolyte that we still don't understand. We haven't quite focused on the electrolytes. There's a lot of research still remaining to be done. I'm highlighting this because a lot of people think that, oh, it reached 400 watt-hours per kilogram at 80% depth to discharge, roughly the cost of this, and it's done deal. It's not. There's a lot of work still to be done to make it compatible, usable in an actual application, and that needs research. Sunlight to fuels, there's a lot of work that has already gone on, and I'll just touch upon very briefly on this. You see, most of the biofuel research that has been done is either using cellulosic biofuels or corn or sugarcane or algae. These are all what I call photosynthetic biofuels. And these are based on the Calvin-Benson cycle in biology to fix carbon dioxide. By its very nature, this Calvin-Benson cycle, I'm sorry it's getting cut off out here, is less than 1% efficient because some of the enzymes in this cycle are corrupted by oxygen as the temperature goes up. The efficiency is really low. It works. It's a great thing. We all rely on photosynthesis, but it's inefficient. And now research is needed. So now you can get all these various groups are looking at ethanol or pyrolysis or biodiesel, and we should do the research to figure out how to make it cost effective. But because it's less than 1% efficient, you need a lot of land, you need a lot of water, and the major cost is in the feedstock collection, is not so much in the processing. And so this is going on, and it all is because of the inefficiency of the Calvin-Benson cycle. Well, what else can be done? Well, you have non-photosynthetic approaches. One is a chemical catalysis. So you can make syngases, you can efficiotropes, and you can make fuels out of that. Or what JCAP is trying, which is an energy innovation hub on artificial photosynthesis, to really understand the science of photosynthesis, which we still don't understand, to be able to split water and make methanol and other carbon-based fuels. There's another one that had not been tried before, which we said it's worth trying, which is the biological catalysis that led to the program called Electrofuels. And the idea is the following, is to really generalize the idea of photosynthesis, but not just rely on photons and not rely on Calvin-Benson cycle, is to use non-photosynthetic microbes and to feed to them various other reducing equivalents, like hydrogen sulfide, hydrogen, directly for electrons, ammonia, and oxidation of iron from +2 to +3 state. And there are a lot of microbes in the deep ocean vents that don't have sunlight that oxidize iron or use hydrogen sulfide to make carbon-carbon bonds. And no one had ever used them. And so the idea was to use them, these non-photosynthetic microbes, to use cycles. Well, Calvin-Benson is one of them, but there are many other cycles that are used which are much more efficient than the Calvin-Benson cycle. 10%, 20% efficient than the Calvin-Benson cycle that had never been used. So we said, why don't we try that and generate some molecules, and if you can get to something called an acetyl-CoA molecule, then you can not only make oil and fuel, but you can also make bioproducts. And this was a crazy idea at that time because while we knew the genome of some of these organisms, We did not know how to manipulate the genomes of these. And people figured this out. And lo and behold, in 2 years, this was the first, now this is a company, OPX, a startup company in North Carolina State, that made the first biofuel without using sunlight. They're using directly electrons to make oil out of this. And this was the first. Now we have 4 or 5 other groups that are making oil out of this, which is phenomenal. And now this is 2 years ago, they made a little vial. Now they're making flasks, and I don't know which way this is going to go. I'm going to share with you another example, which is kind of amusing. We created another program called Petro. So could we engineer plants to make oil directly? Forget about cellulose, this oil directly, and at scale and at cost. And I'll give you one example. So we know that algae can make oil directly, but algae has other problems. The reactors are kind of expensive. It uses water, it gets infected, and all that. So this group in Lawrence Berkeley Lab said that why don't we take the most useful part of algae, that is the metabolic pathway that makes oil, and insert that into a plant like tobacco, and we know the genome of tobacco really well. And so if you can insert it into tobacco, then the idea is that tobacco, which grows in bad soil, can make oil so that you would just squeeze these leaves and oil would come out. And I said, this is amazing, because if this is successful, you would have big oil and big tobacco come together and save the world. I mean, this is unbelievable, right? And I never thought this would actually work, because we said, let's give it a shot. It's worth a try, because it doesn't violate any laws of nature. And what I heard, to my pleasant surprise, is this is actually working right now. And I don't know where this is going, but it always brings a laugh to everyone. So let me just end by saying, this is what I think, this is my personal view of what sustainable growth in the 21st century is all about. We have growth. We have population growth that is happening, and we want economic growth. So think of, this is a very engineer's point of view. You have a black box, and we want growth in the economy, and the population is growing. So this box is becoming bigger, and it needs some input. The input is energy, food, water, material resources. And sometimes we have constraints on the access to it, which we call national security problems, security problems. So that's on the input side. Well, if you feed all this into this black box, it produces some output. And these are emissions and waste. And these are what we call environmental problems. So some people are focused on the input, some people are focused on the output, but I look at it as the same problem. It's the paradigm of this one-way traffic. And this paradigm is what we're stuck with today. And if you really want to change the paradigm, you got to think differently. And no one has figured out how to close the loop in an affordable way at scale. Now you got CO2 emissions from the other side. Could we make fuel out of it? Well, you may think that, well, this violates the laws of energy, laws of physics, thermodynamics, because CO2 is at a lower free energy level than reduced carbon, which is hydrocarbons. That's a high free. Well, yes, that is true. That would violate the laws of nature. So you need some energy. But the energy better not be in this loop, because then you cannot come out of this paradigm, which is why you need some emissions-free energy that is accessible and affordable around the world. And we have not figured this out yet. And that's really what we require for the 21st century. Now, a lot of people say this is impossible. Well, we've heard this before. It can be done if you really put our minds to it. And just to give you a few examples of naysayers, and this is amusing, I want to end with a little bit of humor. There are a lot of predictions, infamous predictions from the past. This is from Sir William Preece, who was the chief engineer of British, was 1870. The Americans have need of the telephone, but we do not. We have plenty of messenger boys. Missed the point. But this is not just from a chief engineer of British Post. This is from a very well-known scientist, Lord Kelvin. Radio has no future. X-rays will prove to be a hoax. Heavier than air flying machines are impossible. Lord Kelvin was opinionated, but he was wrong. And there's a lot of dogma that goes around it. And he's not the only one. He managed to convince Wilbur Wright. Man will not fly for 50 years in 1901. I'm glad he didn't take himself too seriously. Or Orville Wright probably had a better influence than him. So these will go on. And I think it's best, the future is best articulated by Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic. And I think that's what scientists and engineers really have to come together and create some magic for the rest of the world. Thank you.
When you take into account how much energy is used to produce all those things we need to run solar, wind, and other sources, research I have seen says that at best, the total energy we will get out is 5%.
You mean the energy?
Energy left and energy we will have will be at best 5% of energy that we really need for our consumption. It's based on US data. So is that number higher or promisingly higher? Or is all that media hype that solar, wind is really energy future just a false hope for the total energy?
From what I understand, you're saying that the energy that goes into making solar cells and what energy comes out, the net output is 5%. Is that what you're saying?
No,
the life cycle?
It's when you get energy out of all of that, all the energy that we need, contribution of that part will be only 5%. And we still need 95% of energy for sources we know as nuclear, fossil fuel, hydro. So we are talking only about 5% of energy we will be able to harvest and use.
I think, there's no question that there is no silver bullet in this. Because you certainly need nuclear. And we were asleep on the wheel on nuclear for 30 years. And you really have to energize. And now we have a few plants that are being built today. Frankly, this is not just a US problem, it's a global problem. China is building way more, which is a good thing. But they're also building way more coal-fired power plants at a faster rate than the nuclear plants, unfortunately. The nuclear cost has to come down. The financial risk has to come down, and which is why the whole thing that we started on small modular reactors. And so that needs to happen because there's a financial capital exposure that happens at gigawatt scale that does not happen at hundreds of megawatt scale. And so that needs to happen, but that's still the same technology as before. It still needs to go through the NRC. So there's no question that if you have to address climate problem, you got to have nuclear in the mix. But think about it this way. If you look at nuclear is a centralized source. It needs the grid to transmit the electricity to somewhere. There are 1.5 billion people in the world who do not have access to the grid today. And it is unlikely that people will have that access. The grid will go to every human being. Unless there's a massive urbanization that happens, everyone flocks to the urban cities, which will be a disaster. And that may happen, but that'll be a disaster. So there is need for other sources of electricity, not just nuclear, that'll enable people to grow grids in localities where the traditional grid does not go, but have a microgrid and have a solar panel and some batteries to really provide the electricity when they need, because electricity use completely changes the lifestyle and the quality of life of people, productivity of people. So I think there is need for many of these, not just one.
Other questions? There's one here.
When you showed the plot of the cost of various generation facilities, did that include subsidies? And I'd also like you to comment generally on subsidies that exist now and their path going forward. You know, should we remove them? Should they be there, et cetera?
Great question. These costs included subsidies. Our sunshot goal is subsidy-free, which is trying to get to 5 cents a kilowatt hour at the utility scale without subsidies. And that's a hard problem. But if you look at solar, we have investment tax credit of 30%, which in 2017 will get to 20%, get to 10%. And I'm hoping that the cost would come down far enough by 2017 that will compensate for the reduction in the subsidies. But here's what I think of subsidies. The role, and this is where there's a lot of debate and controversy, what is the role of the government? And the role of the government is to create options and to give choices to increase the competition among various players and let the market then play out, right? So if there is any new technology that is out there, new technologies generally are more expensive because it is the early part of the learning curve, whereas mature technologies. So if you do nothing, they'll never be able to compete. Because in the financial sector, innovation is a risk. Not among scientists and engineers, but in the financial sector, it is a risk. So you've got to reduce the risk in some way. So what you really have to look at is where the learning curve is going in a subsidy-free way, and when is it going to intersect with the unsubsidized cost of other mature technologies, and provide the subsidy for that finite amount of time in a ramped-down fashion with a signal there for the business community so that at some point it would be competitive in an unsubsidized way, and then remove the subsidies. That would be the right way to do it. Now, of course, in the United States, we don't do it that way. We have production tax credits for wind, which go up, and then next year it goes down, and then we go up, which is, from the business community, that's completely unpredictable. And they would rather have a signal, long-term signal, like the CAFE standards in transportation. We have 2025, 54.5 miles per gallon corporate average fuel efficiency. Now that's a signal. And now all the innovators are now pulling their hair, and the ones who can innovate will win. And there are many ways of going there. And I think so that's the kind of policies that we need to put in place to enable some of these new technologies to come in and compete in an unsubsidized way in the long term.
Along the questions of policy, we just had, we're in comment period with the EPA in terms of CCS versus CCU. Basically, we have a reduction in carbon emissions, and the only way to meet the goal is by doing sequestration. The reuse, which you mentioned towards the end, will not qualify. And EPA set the rule. DOE's actually been relatively silent. We need basically the business community to say, yeah, we need to look at it a life cycle approach, that this is the net CO2 emissions if we do just say carbon capture going to algae rather than to sequestration. But that's not, basically it's not on the radar screen at all. Is there any work coming along in terms of commenting on that?
Well, I think it's very difficult to do CCS today without a carbon price. I mean, what's the incentive for the business community to do that? Now, carbon capture utilization is predominantly for enhanced oil recovery. And the price that oil companies are willing to pay today, by the way, there's a shortage of CO2 in the United States because the only sources of CO2 are not by capture, but by these natural formations, Colorado, there's the pipelines, et cetera, to Texas. So the price they're willing to pay is about, and it changes, it's about $30, $35 a ton. So unless the cost of carbon capture is reduced below that, there is no business in the absence of a carbon price. So, I mean, frankly, if you really want CCS or CCU or whatever that may be, you got to have a carbon price. Otherwise, the business community is not incentivized.
But the way the EPA ruling, we're going to have a different carbon price for CCU, which will be zero, versus CCS, which will be real, because that's the only way to meet the mandate. And so we may see a gap, and we'll see a loss of investment in the algae pathways.
Well, I mean, oil from algae is expensive today. And I think if they can reduce the cost of, I mean, we can go offline on this, but frankly, today, the cost of oil production from algae is about, I don't know, you can correct me if I'm wrong, but north of $5 a gallon. And it's very hard to do, carbon capture because the impedance match really is not there today. So we have a carbon, I mean, at the end of the day, I know we're not going to get it right away, at least in the next few years, but we need a carbon price of some kind. Otherwise, none of these things would really flourish and grow. That's my humble point of view.
Okay, on that, that's a great way to end, actually. So let's thank Arun once again for a great talk.